So the classical ciphers, last week we mentioned Caesar cipher, and that led to a brute force attack, where a brute force attack involves not using our brains but just trying every possible key. And it works in the Caesar cipher because there are only 26 possible keys. So we can try them all, and this brute force attack is successful because if we take the ciphertext and decrypt using every possible key, then we'll be able to detect of all those possible plaintext which are produced. So we decrypt a ciphertext with a key to get a plaintext value. We'll get 26 possible plaintext values. Only one of them will make sense. All the others, the other 25, will look like just random arrangements of English letters. And that generally holds that when we decrypt something, if we use the correct key, we'll get plaintext that we can recognize. It will have some structure that we can recognize. If we decrypt some ciphertext using an incorrect key, and by incorrect key I mean a key that is different from what it was used for encryption. So if we decrypt with an incorrect key, we'll get plaintext which is random looking. It doesn't have a structure. And we'll assume as the attacker we can recognize that because we get plaintext which doesn't make sense, we use the wrong key. Okay? So as we try different keys, if the plaintext doesn't make sense, assume that's the wrong key. Try the next key until you decrypt the ciphertext with a key that results in plaintext that makes sense. And it turns out in practice, in most or if not all applications, that's true, that decrypting with the wrong key gives us random or recognizably wrong results. Decrypting with the correct key gives something we can recognize as correct. We then went on to, so that introduced the concept of a brute force attack. We mentioned a different cipher where basically we have the 26 English characters and allow the person encrypting to choose an arrangement that each of the input plaintext characters will map to one of the 26 possible English characters. For example, A, when it's encrypted, will become D in the ciphertext. B will become Z, and Z will become Q as one possible encryption mode. But the people encrypting and decrypting choose that arrangement, and they must let each other know what that arrangement is. And we saw that in that case, the number of arrangements possible is 26 factorial. In effect, there are 26 factorial possible keys, because from the attacker's perspective, we don't know this arrangement. The encryptor chooses it. We need to find that arrangement that produces the correct plaintext as the attacker. And then since there are 26 factorial possible arrangements, then from a brute force attack, the attacker would need to try 26 factorial possible keys. And then we saw, if we jump back, we flicked between a few of these slides, some of the concepts versus some of the examples. If you look at the bottom line here, and it's a bit confusing, someone asked me a question. This 26 factorial is really, this last line is a special case. It's in the wrong column. 26 factorial is the key space. The key space is the number of keys. The key length is only relevant for the binary keys, so the first 6 rows in this table. We'll return to them later. It means key length is 32 bits or 256 bits. 26 factorial doesn't mean the key length, it's the key space. So those two should be really in the same column. 26 factorial is approximately 2 to the power of 88. 26 factorial, if we need to try all of those keys, if we have a computer that can try keys at a speed of 10 to the power of 15 keys per second, so what's that, 1 million billion keys per second, then it would take 10,000 years to do a brute force attack. So this shows that it's quite easy to defend against a brute force attack. Brute force attacks, in theory, are easy, try all keys, but in practice, we can make a system secure against a brute force attack by just making the key large enough. Make sure the key space is a size such that even with the fastest computers today, and even with millions of those fastest computers, someone still won't be able to find the key because there's not enough time. And we'll see that with practical keys today, that the key length is such that brute force attacks are not possible. Back to some of our classical ciphers. So the monoalphabetic cipher, this substitution cipher, brute force attack not possible. But it turns out it's very easy to break using what we say crypt analysis. And we exploit the fact that the plaintext has some structure in it. In particular, the language, English language, and the same with any other language, has some letters that occur more frequently than others, some diagrams that occur more frequently than others, so diagrams are pairs of letters, and trigrams and words even. So what we do is we look at the ciphertext, look at how the algorithm works, and try and work from the given ciphertext back to the plaintext, and in the same time discovering the key. It's quite hard to show in the lecture such an attack, but one of your homework tasks from last week was to do some reading. And if you skip forward a few pages, I give you the printout of the web page where I give an example. This is the example. I'll browse through it, but it's easy to see which page. I think in the printouts. Page 21 in your printouts. It's called Classical Ciphers and Frequency Analysis Examples. So it's easier for you to read on paper than on the screen. But it just steps through some simple examples of attacks on different ciphers, starting with a Caesar cipher and a brute force attack. So it starts with this DVVKZEC is some ciphertext. The attacker knows the ciphertext. They know Caesar cipher was used. A brute force attack really involves looping through all 26 possible keys. And you'll see it on yours that, all right, I just used some software to decrypt, just a script to decrypt, and I tried all 26 possible keys, and we see one of them makes sense. Where is it? 17. Meet in lobby at 10. Okay, so all the others don't make sense. So this is a brute force attack on Caesar cipher. The next thing is, and again you should read through it in more depth than what we can cover today, is the fact that some text, some large piece of text, a book or a set of books, will contain some letters occurring more frequently than others. So in this example, I used some software to count the letters in an example book. So I downloaded a book from a website in text format, and this program, Crypto Count Letters of that book, %sort, just counts the letters and sorts them from the largest percent down. So it returns that the letter E occurs 12% of the time in the text. The letter T, 9%, and so on. And if it only shows the first 10 or so, 10 or 15, you can find for the rest as well. Just showing that in a large text with a lot of words, you'll probably find that the letter E was usually the most frequent letter in English. T and A are up there as well. Of course, in different texts, especially as they're shorter, those frequencies will change. But if you cover a large set of text, you'll see some pattern there. Q, X, and U are quite, or maybe Q and X especially, are quite infrequent down the bottom. Same with any other language. In Thai, in other languages, there's some structure. Some characters occur more often than others. Also, we can count the digrams, and we see that TH occurs most often, HE, IN, ER, and other digrams, pairs of letters, which are not shown, are much more infrequent. And trigrams is the triples, THE, AND, ING. I think you see in words and in phrases, those triples occur more frequently than others. Just going back to letters, if every letter occurred at the same frequency, what percent should we have? What percent of E's should we have? If every letter was equally distributed across the text, what percent of E's or T's would we have? 1 divided by 26. So we have 26 letters. If they were equally distributed, then we'd have 1 divided by 26 as a fraction, which is about 3.85%. So if the letter A occurred at the same frequency as Z and Q and R, then that would all occur about 3.85%. So they'd all have about the same value. But of course, in this case, in practice, some are more frequent than others. That's in the plaintext. And the example here, another ciphertext, again using Caesar cipher, and again it's hard to see on the screen, but a longer ciphertext here, not just a few words, but several sentences, I think it was. Again, we could do a brute force attack, so that's possible on the Caesar cipher, but we can do some form of frequency analysis. So what we do is we take that ciphertext at the top, and here I count the letters of the ciphertext, and I see J occurs most frequently at 13%, Y is 9%, S is 9%, and so on. From that, we can almost work out what the key is using the Caesar cipher. What is it? How do we work it out? How do we work out the key? In the ciphertext, the most frequent character is J. In the original plaintext, we'd expect the most frequent character to be E, because in large plaintext, we know from the statistics that the most frequent character is E. Not always in short plaintext, but it's a good guess to say, okay, if the most frequent letter in the ciphertext is J, most likely that corresponds to E in the plaintext. So we find in the Caesar cipher what would shift us from E to J. What is it? I think it's here, a key of 5. J is the most common letter in the ciphertext. We expect the most common letter in the plaintext to be E. That means if we need to map using the Caesar cipher E to J, it's a shift of 5 positions. So a key of 5. And we actually try it with a key of 5. That is, so by guessing the key of 5 just from that analysis, we decrypt immediately. So this is not brute force. We don't try all keys. We deduce the key, try it, and it turns out that, yes, it does produce some text that makes sense. Okay? So this is crypt analysis. It's not a brute force attack. Instead of trying 26 keys, we've cut it down to trying just 1 key plus a little bit of analysis of the frequency of letters. It works quite well with a Caesar cipher. The reason it works is because, just going back to the Caesar cipher always maps one letter of plaintext to the same letter in ciphertext. So if there is a plaintext message which has 12% E's in it, then the ciphertext, if we use this form of the Caesar cipher, if the plaintext had 12% E's, then the ciphertext must have 12% H's. Okay? If we use this example Caesar cipher. a key of 3. So therefore, if we count the letters in the ciphertext and we get about 12% of the letter H, then we guess, all right, H maps to E, and that gives us a key of 3. So Caesar cipher is both insecure with respect to brute force attack and insecure with respect to crypt analysis. The next example on that web page, again, I highly recommend you reading through it because it's hard to see on the screen. Remember, a monoalphabetic cipher takes 10,000 years for the fastest computer to break in brute force attack. So brute force is not possible. But a crypt analysis turns out we can do in 10 or 15 minutes by hand. Okay? And this goes through the steps of doing such analysis. So again, we start with some ciphertext. The attacker has some ciphertext. It's listed there. We know that it's the monoalphabetic cipher, but we don't know what mapping, what arrangement of letters were used. We need to find that out. So what we do, given the ciphertext, count the frequency of letters. And we count them when we find out T is the most frequent. Z is next, and O. What's your guess now? Maybe T in ciphertext maps to E in plaintext, because we see T is the most frequent letter in the ciphertext. We expect E to be the most frequent letter in the plaintext. So in terms of the mapping, E, when it was encrypted, could have become T. It's not always true, but usually one of those top frequent letters, E, T, A, and N, map to one of the frequent letters in the ciphertext. So we do a little bit of trial and error. Take the ciphertext, replace all the letter T's with a letter E. And then do that for the others. That is, maybe Z in the ciphertext maps to, if we go, what? T. So the top 4 or 5 in expected plaintext, E, T, A, O, I. What we get in the ciphertext here is T, Z, O, L, G. So we could try those mappings and then look at the ciphertext and start replacing the letter T with E. Replace the letter Z with T and see if we start to see some words appear in the ciphertext from decrypting to get the plaintext. Sometimes it works quickly, that is T does map to E. Sometimes we find it doesn't make sense, we need to try something else. But with a computer you can do that quite easily. We can also do it with diagrams. What was the most frequent expected diagram? Remind me? TH, okay. We measure in the ciphertext, we get OF. Maybe pairs of letters in the ciphertext, OF, correspond to TH. So try and replace them and see if we start to build up words in the ciphertext. And that's what we do here. It's hard to see, but this is the ciphertext, but I've replaced some letters with uppercase letters, which are the corresponding plaintext if I map according to our frequency statistics. That is, the letter here which was, I think, T in ciphertext, I've written it as E in plaintext. Doesn't give us much clue as to what the message means yet. That was just replacing T with E. But we do it with the other letters. And we keep trying. We map T to Z, or what was input as Z becomes T. And I go through, you can go through a few steps, try some others. And then you may start see, if you know what you're looking for at least, some patterns. THI, INT, they are common things we'd expect to see in English text. T-H-E, I-N-T-E something N-E-T. What's that? Internet. Okay, so if you have some context, or you can guess what the message may be about, you can start to detect words. So that suggests maybe the letter K maps to R. And we can try that and replace all the K's with R's and keep going through a few iterations. And we see something, this, something, something, and so on. You see the word internet there. Return and try some of the more frequent letters, and if you keep going, it doesn't take long, a few more steps, and you get to here. This course, something, introduce, okay, to the secure it. Okay, so you basically have it now because you're starting to see words, and because you've got most letters in a word, you can start to work out quite quickly what the remaining letters are. And the next couple of steps you've almost completed, and you get to the end. So our original plaintext. All right, on pen and paper it takes a few steps, and it takes more than 10 or 15 minutes, but with a computer it's almost instantaneous because a computer can do that quite well as well. It tries different mappings, and it looks for common words. So if we do a mapping and we get words which are in the dictionary, then it's most likely the correct mapping. If we get words that are, or we get sequences of letters which are not words, then it's likely an incorrect mapping. So we can program a computer to do that for us. So a monoalphabetic cipher, brute force, impossible. Crypt analysis, easy. Trivial, really. Again, have a look, read through that one in more depth as homework. Monoalphabetic is not secure, despite a brute force attack not being possible. The problem with it is that the frequency of the plaintext, so the fact that E is the most frequent character in the plaintext, maps directly to the ciphertext. So if there's one character, E is the most frequent in the plaintext, then there'll be one character in the ciphertext which is the most frequent. So we just need to find out which one, and then we can start trial for the other frequent characters. So the ciphertext, when we encrypt our plaintext, contains the frequency statistics which are present in the plaintext, and that's bad. So there are ways to improve it. Encrypt multiple letters of plaintext at a time. So instead of take one letter, letter A, and map it to Q, for example, take a pair of letters. TH encrypts to ZF. Or take a triple of letters and map it to another triple of letters. That starts to spread out the statistics in the ciphertext. Or to, as we'll see in another approach, use multiple alphabets. So instead of a monoalphabetic cipher, a polyalphabetic cipher. So we'll see both of them in the next few examples. This just gives another viewpoint of the most frequent letters. I think this was taken from many legal texts. So hundreds of thousands of words of text, and they count the letters. We'll come back to this one to compare some of these ciphers later. So let's look at a cipher that doesn't operate on each letter at a time, like the last two we saw. It operates on a pair of letters. And that can help to spread the statistics in the ciphertext so that one letter which is frequent in the plaintext doesn't map to one letter which has the same frequency in the ciphertext. It's called the Playfair Cipher. Let's go through it. There's two steps. We do some initialization where we create a matrix. So again, we use English letters. How many English letters are we? How many do we have? 26. We create a 5 by 5 matrix, gives us 25 characters. So we need a special case. We've only got space for 25 letters. Which one are we going to remove? in this. So we need to agree on which one we'll remove. And typically, or the original version of Playfair said, let's treat I and J as the same letter. Because often in plain text, you'll be able to recognize that, okay, by the context of the word, whether that letter is supposed to be an I or a J. Okay. So this is part of the algorithm saying, in our plain text, if we see the letter J, let's just change it to I. And we'll see it still works quite well. So what we do is we write down a 5 by 5 matrix and we choose a key word in this case. Not a number, not a single character, but a word. And we write that word row by row. And then, so if our word is 4 letters long, it's the first 4 columns on the first row, then the remaining 21 entries in our matrix are the alphabet. And we make sure that we do not repeat any letters. Let's try. And you'll see that's not so hard. So just the initialization step first. So the two people communicating, they must have a keyword. So that's the secret that they share. They both must know that keyword. No one else knows that keyword. So we start, what have we got? The keyword in this case, and maybe it's on the election notes, I can't remember, but Thailand. So that's our secret that the two users choose. The attacker doesn't know that. So what we do is we write that in a 5 by 5 matrix. T H I T H A I L, and we make sure we don't repeat any letters. So we've already got an A. The next letter is an A, but we've already written it in the matrix, so we skip this next A and go to N, D. So there's our keyword written in the matrix. Don't repeat letters. And the rest of that 5 by 5 matrix we fill out with the rest of the alphabet in order. We've already got A, so we go through A, B. All right, we need to make sure we skip the letters that we've already got in there, so we don't do D again. We've got H, so we go to K. We've got J. Here's our special case. I and J, think of them as the same letter. So we don't write a J here. Because we can only fit 25 letters in our matrix. Okay? This is the way the algorithm works. We're going to use the matrix to encrypt in a moment. So we need to really remove one letter. And one decision is to say, okay, let's remove the letter, or let's join the letter I and J. So we'll see later, if we want to encrypt the word which has an I in it, then we'll use the I in the matrix. If we want to encrypt the word which has the J in it, we think of it as the letter I in the matrix. And when we decrypt, the user will be able to recognize whether the letter that we get in the plaintext is supposed to be an I or a J. Because there are not many words where it would be confusing whether the letter is I or J. If you replace a word which has an I with a J, that word won't make sense. If you replace a word which has a J with an I, that word will most likely not make sense. So you'll be able to use the context of that word to distinguish which one is which. We'll see in some examples. Let's fill in the matrix. What do we get to? O. Almost there. V. So there's what we call our Playfair matrix. Playfair is it's named after some guy who I think it was some general that they named it after. That's the initialization. Now when we want to encrypt something, we use this matrix to encrypt. So the person who's encrypting can create the matrix, and when someone wants to decrypt, they create the same matrix. Okay, so the person who decrypts knows the keyword is Thailand. They create the matrix in exactly the same manner. So as a simple example, we'll start with the plain text of the word hello. We want to encrypt hello and get some ciphertext, just to show you how the algorithm works. The Playfair Cipher operates on pairs of letters. That is, we look at a pair of letters of the plaintext at a time. How many letters in our plaintext in this case? 5. We don't have an even number. If we're going to have a pair of letters at a time, we actually need an even number of letters. So we need some special cases in this algorithm to say, if our plaintext has an odd number of letters, add some padding to make it an even number of letters. And a common way to add padding is to add a letter on the end such that someone will still understand the message. Maybe add the letter X on the end, and you get hello X as the plaintext. Still, someone who receives that will most likely understand that it means hello. Okay? And when you have much longer plain text, it's not a problem if you add one letter at the end, because someone will still be able to read the entire message. But the algorithm works on pairs of letters, so we must make sure the plain text has an even number of letters. But there's another special case, which we'll see in a moment. But let's show the general case. What we do is we take a pair of letters at a time, and our first pair is HE. So down here, the first pair is HE. We look up those letters in the matrix, and we find the positions of H and E. And to encrypt that pair of letters, we find, so for H, we find the letter which is on the same row and as H and the same column as its partner. So the same row as H and the same column as E is the letter L. So it's going to encrypt, and I'll write it as uppercase here because often we write ciphertext as uppercase just to make it clear. This is ciphertext, this is plain text. H, E maps to L, D. So look at the pair of letters of plain text, and the one on the same row as ours and the same column as our partner becomes the output ciphertext. The same row as H, or the first letter, H, and the same column as the second letter, the output is L. Then for the second letter output, the same row as E and the same column as H, outputs D. So that's the first, we encrypt a pair of letters at a time. So we encrypted the first pair. Try the next pair. What happens? What is the next pair of plaintext letters? LL. That rule doesn't work, okay, because the same row as L and the same column as L is L. And we'd encrypt LL to LL, which is not very good encryption not to change the plaintext. So in fact, we have another special case. If we have a pair of letters which are the same, separate them. And we separate them by introducing some padding. So in this case, the first pair was HE, the second pair would be LL. We recognize, well, we can't do that. So let's introduce some padding here. Let's introduce another letter, a special letter, let's say X. So it will become HELXLO. And that's nice because it also gives us our even number of letters. So we've got 3 pairs. So that's needed if we have in a pair the same 2 letters. Because if we used our rule on the same 2 letters, we'd get the same output ciphertext. So in fact, to encrypt hello, the next step we do is we take LX, so we had LL, we introduce the X there, and encrypt that. What does it become? All right, L, X, same row as L is A, and same column as X. So it becomes ciphertext A, and the same row as X, the same column as L, we get Z. And the last one, what have we got? LO. What do we get? Here we need a special case. LO is the next pair, the last pair of plaintext letters. And we look at the matrix and we see L and O are on the same column, in that case, just move down, wrap around if necessary. So LO, what's down from L? E. What's down from O? U. Becomes EU. If our 2 input plaintext letters are on the same row, move to the right. If they're on the same column, move down. If not, find on the same row as our letter and the same column as our partner letter.
What if we are encrypting L and E?
LE, then it will become what? EO. So LE, we think of, if we have LE, L becomes E, E becomes O. If we're encrypting QU, Q would become R, U would become P. It wraps around. U, Z, Z, L. Okay. Wrap around on the columns and on the rows. And we have our ciphertext. So that's our ciphertext we send to our friend. Our friend receives LDAZEU. Our friend knows the keyword is Thailand and creates the same matrix and applies almost the same rules to decrypt. The same rules except when we're on the same row or column, instead of moving down from what? EU to decrypt, we'll move up. EU will become LO when we decrypt. We need to get the original plaintext back, which was HELXLO. In these simple ciphers, I'll usually not go through the decryption, but you should try them. Decryption is easy to test. If you decrypt and get the original plaintext back, it's correct. If you don't get the original plaintext, you've made a mistake, especially in your quizzes or in the exam. It's very easy to test if you've got it 0 marks or full marks. Just encrypt it and decrypt it, and if you get the same answer, you're okay. With these ciphers at least. What's important in this cipher, what's different from the others, is it's operating on a pair of letters at a time. And we'll just write it again. Our plain text we needed this X to make it, to separate the L. So think of the plaintext like this. But we know it means hello because there's no word hell XLO. So we can guess X is a special character. And we got ciphertext LDAZEU. Look at the mapping from one letter of plaintext to one letter of ciphertext. Look at the L's. The first time we encrypt the L, the output is A. The second time we encrypt the L, we get an output of E. That's important. And that's an important characteristic of this cipher in that it makes it harder to do that frequency analysis of letters. L occurs, I'm not sure if it's on one of the slides. Let's go back. L occurs about 4% of the time in plaintext. With a monoalphabetic cipher, Caesar cipher, L would map to the same letter each time, and that same letter would occur about 4% of the time in the ciphertext. But in the Playfair cipher, even though L may occur 4% of the time in the plaintext, all right, here's it's quite short, so we can't look at percentages, but in a long plaintext, if L occurs 4% of the time, the letter we get out from encrypting L doesn't necessarily occur 4% of the time because L maps to multiple different letters. Okay, and that makes it better to withstand someone doing an attack that looks at the frequency of letters, because now we really spread out the frequency of letters. One letter doesn't always map to the same letter. It maps to different letters. And the same concepts can be applied by applying our encryption across different lengths of characters, 2, 3, and so on. It works better when our plaintext is much longer. So that's the strength of the Playfair cipher. But we still have the frequency of diagrams. Diagrams are pairs of letters. So if later we have HE, we have a very long plaintext, later there's a HE here, it will still become LD. If later we have an LO, we'll get ciphertext EU. So diagrams still map to the same ciphertext, but single letters do not. And an attacker can use the fact that some diagrams occur more frequently than others. TH, EN, IN, and so on. And again can break the Playfair cipher with a little bit more effort than the monoalphabetic, but nothing that a computer cannot do. So it's better because it doesn't map one letter of plaintext always to the same letter of ciphertext, but it still has limitations because pairs of letters always map to the same output. We did that. It's better than monoalphabetic, but for computers, once you look at diagrams, trigrams, expected words, it's very easy to break still. So what we need for a strong cipher is to make sure the ciphertext contains no statistics that make it easy for the attacker to work out the original plaintext. And that's what we're moving towards now. We saw with the monoalphabetic cipher, and I'll jump back to it, we map one letter always to the same ciphertext letter. A always maps to D in this example. Y always to F. So if our plaintext has 12% E's, our ciphertext will have 12% S's in this case. And that's bad from the strength of the cipher. It's easy for the attacker to use that frequency of letters. What we want is that the letter E, even though it occurs 12% on the plaintext, then it doesn't map to the same letter each time, and in fact that it distributes the letters amongst those 26. So sometimes E maps to A, sometimes it maps to B, sometimes through to Z, so that there's an even distribution of the letters in the ciphertext. Ideally, the ciphertext should have no letter occurring more frequently than any other letter, and that would be a perfect cipher. And the way to achieve that is to allow a cipher to map to multiple different letters, called a polyalphabetic cipher. And we'll go through two examples, Visionaire Cipher and the one-time pad. And there's another one in the textbook, but there are others, but we'll just go through two to demonstrate these. The Visionaire Cipher. Think of it as 26 different Caesar ciphers. Remember, the Caesar cipher says take a letter, take the key, and shift that letter by the key number of positions to the right to get the ciphertext. Well, we've got 26 different keys we can use. So what the Visionaire Cipher does is we have, instead of one key, we have one key letter for each input plaintext letter. We actually have a key word. So the example here, if the plaintext is Internet Technologies, the key word in this example, Sirentorn, what we do is we repeat the keywords such that we generate a key which is the same length as the plaintext. So I repeat it. If we don't have to complete the keyword. So if we had AND here in the plaintext, the key would be SIR. So we just repeat it until we fill out such that the key is just the keyword repeated, but the key is the length of the plaintext. Then to encrypt, we take the plaintext letter I and we apply the Caesar cipher, where the key is S. And if you take the Caesar cipher, input plaintext I, key of S, you can check, you get A as output. Then the next letter, N, is the plaintext letter in the Caesar cipher. The key in the Caesar cipher is I, we get V on output. And we keep encrypting using the Caesar cipher, but instead of using a Caesar cipher with the same key for every letter, we change the key according to the keyword. Everyone can decrypt Caesar cipher, Visionaire cipher? Common quiz question. Quiz questions are usually not encrypt but decrypt because they are harder. A, you need to know the algorithm, and B, sometimes they're harder, but they're easier for you because you can check the answer. Okay? If you decrypt a ciphertext and you get random letters in the quiz, then most likely you've done it wrong. If you decrypt the ciphertext in the quiz and you get a word that you understand, then most likely you've done it correct. But in this case, to decrypt, we again use the Caesar cipher. If we have the letter A as ciphertext, we know the key is S, we use the Caesar cipher with a key of S and do the shift back to the left by S positions. S is what? 19 or 20. The point of this in terms of security is that if we look at our plaintext letters, look at the letter T. It occurs 3 times in this short plaintext. T here, and there's 2 T's together. And look at the letters in the ciphertext that it maps to. The third letter T, I-N-T, becomes K. The next T becomes H. This T becomes K again. So we've changed the letters in the ciphertext, except here we've got a K again. And we'll see that that's a flaw in this cipher. Let's try other letters. E. There are 4 instances of E. E becomes M, L, R, and V. So even though E is the most frequent letter normally in plaintext, using the Visionaire cipher, it will not map to any one letter in the ciphertext, meaning it's hard to work out what is the mapping from the ciphertext letters back to the plaintext letters. So it's all about making sure this ciphertext doesn't contain the statistics of the language. It doesn't contain one letter that occurs 12% of the time, and this starts to achieve it. If we especially have a much longer plaintext, we'll see that occur. We could count the number of A's. How many A's should we get? What percent of A's should we get in the ciphertext? 1 in 26, ideally, 3.85%. And the number of B's in the ciphertext should be 1 in 26 if it works well. Okay, so that's what we want, that the ciphertext appears random. There's no distribution of the letters. One doesn't occur more frequently than the other. And this is starting to achieve it. It's almost perfect. The problem with this, especially when we have large plaintexts, which is usually the case when we're communicating, we don't always just send small messages. We usually send a sequence of messages or some long messages. The problem is that we need to repeat the keyword. And it can turn out, as we repeat the keyword multiple times, we do start to get some letters in the plaintext mapping to the same letter in the ciphertext. And that's bad. We'd like the plaintext letter to always map to a different letter in the ciphertext. But the repeating keyword doesn't allow that, especially for long plaintext. So this is a much better cipher than what we've seen with the monoalphabetic cipher and even the Playfair cipher, but it's still possible to break. And we will not go through an example. You can get software that will do it for you quite easily, and you can do it manually, but you need to look for the fact that a keyword of a particular length that starts to repeat, and therefore you'll start to get repetitions in the output ciphertext related to how long the input keyword is. So it is quite easy to break using a computer. The weakness is that we use a structured keyword. Why did we use a keyword? To make it easy for the two users to exchange a key. I just know the keyword and I tell my friend, and it's easy to remember and to write down. A better way is to not use a keyword but use a random sequence of letters. And that's the next cipher, the one-time pad. Almost the same in this example, but instead of using a keyword and then repeating that keyword, choose a random sequence of letters which is the same length as the plaintext. If our plaintext is 1,000 letters long, choose a key which is 1,000 letters long, such that those letters are chosen randomly. If we do that, then we get a perfect cipher. The one-time pad is the only known scheme that we consider unbreakable. And we'll talk more about what unbreakable means after this and when we return to some other slides, but there's no way to break it if we do it correct. Even a brute force will not defeat it. Even if we have all the computers and all the time in the universe, we cannot break it. So we'll see some reasons why later. But first, how does it work? Well, we won't go through an example because it's the same as this, but instead of using the keyword, just choose random characters here. But make sure they are random. Okay, so you need to correctly choose random characters. You can't maybe just pick them from your head. You need a computer to correctly choose those random characters. If you do, even if there's repetitions of letters in the plaintext, we will successfully spread out the frequency of letters in the ciphertext. For a long plaintext, the number of A's in the ciphertext, it'll be 3.85%. B's, the same frequency, 3.85. Z's, 3.85%. That is 1 out of 26 of the letters will be each of those letters. So what we've gone through is 5 different classical ciphers to try and demonstrate some of the key concepts used in encryption, even in real ciphers today. The point is, try and get the ciphertext which has no structure, even though the plaintext has some structure. Get the ciphertext to appear random. Questions? Let's go on through those ciphers quickly. A lot of new concepts. Some questions. You should be able to encrypt with each of those 5 ciphers. Caesar, Monoalphabetic, Playfair, Visionaire, one-time pad, and similarly decrypt. Caesar cipher, okay. You can encrypt, decrypt with Caesar cipher? Yes, okay. What about Playfair? That one made sense? All right, you may need to practice a little bit before you remember the steps, but once you practice the ciphers once or twice, I think you'll work it out. Vigenere. Everyone can encrypt with Visionnaire Cipher? If you can do Caesar Cipher, you can do Vigenere, because it's the same. It's just that we change the key each letter. Let's try it, just to confirm. We'll just do the first 1 or 2 letters here, INT, SIR. What do? We have plaintext. I. And we have the key S. And I'll bring up the numbering of letters so it's easy to do quickly. Hard to see, but we see that I is 8, S is 18. So Caesar cipher, what do we get? Encrypt. I is 8, S is 18. I is the 8th letter, S is the 18th. Caesar cipher, add them together and then mod by 26. 8 plus 18 is 26, mod by 26, we get 0. Or A. Okay, it's just the Caesar cipher. N is in fact the 13th, or letter 13. Just do this one. I is 8. So this is the I is the second letter in our keyword. And we get what? 21. Mod 26 is 21 and the 21st is V. Okay? And you can keep going. So it's the Caesar cipher. The ciphertext A, V, and if you keep going, K, M, and so on. So you can do the Caesar cipher. Monoalphabetic, it's hard to do in practice because you need to write down all 26 letters, but it's not so hard. Playfair, you need to practice a little bit. Visionnaire, well, if you can do Caesar Cipher, you can do Visionaire. Just remember it's the keyword repeats. And one-time pad, exactly the same as Visionaire, but the keyword is no longer a repeating word, it's just a random set of characters. So, exactly the same procedure. Any questions before we summarize on the concepts that we've learned?
So one-time pad is unbreakable, but we still need to find a way to transport the key securely.
Right, let's look at these trade-offs and the security. So we arrived at the one-time pad. It is very simple. In fact, there are different implementations. The implementation we see of using the Caesar cipher is what we use on English characters. But for a computer, when you're operating on binary, you can just use an exclusive OR. It turns out that if you take your binary plaintext, you exclusive OR with a random sequence of bits of the same length of the plaintext, you'll get the same effect as, or you'll get the one-time pad. You'll get a perfect ciphertext as output. So it's actually very easy to implement in hardware. XOR is very fast in hardware. We call it unbreakable. And we'll see on one of our earlier slides, we'll define unbreakable as meaning unconditionally secure or unconditional security. Under no conditions can we break it. We cannot use the frequency analysis to try and work back. We cannot look at diagrams and trigrams because there is no diagrams or trigrams that occur more frequently than any others. And there are no letters that occur more frequently than any others in the ciphertext. So there's no way to take advantage of that structure in the plaintext. Can we do a brute force attack though? Even I give you all the computers in the world and I give you all the time in forever, okay? As much time as you want. Let's say you have a computer with infinite processing capability. So it can instantly try all possible values. Will it work?
Yes, but you wouldn't know the right.
Right. You can try all possible keys. So assuming you can try all possible keys, and there are many, many keys possible, so we need enough time, but assuming you could try all possible keys, still you would not find the plaintext. And the reason why is because what you'll do is you take your ciphertext, decrypt, and you get some potential plaintext. You decrypt with one key, then you take the same ciphertext, decrypt with a second key, get the second set of potential plaintext, and you do it with all the possible keys. That's brute force. So you'll get many possible plaintext values. And then we said you need to choose the one which makes sense. Okay, say the English words. Well, it turns out that there are so many keys such that if you try all the keys, many of the possible plaintext values will make sense. There won't be just one that is an English phrase or an English sequence of English words. There'll be many that make sense. And then the attacker has no way to determine which one is the true message. Because if you get many, say, English words or English sentences that make sense, how do you know which one's the true one? And there's no way to know other than guessing. And in practice, there'll be many such that a guess gives almost a zero chance of guessing. So even if you had a brute force attack, you had enough time to do a brute force attack, you still wouldn't get the plaintext. And that's what we mean by unconditional security. A brute force attack doesn't help. This is an example of that concept, but just with two keys. So this was the ciphertext. Okay? The attacker knew the ciphertext. The attacker did a brute force attack. They tried many possible keys. 2 keys they tried, of all of them, I only list 2, they tried this key. To make it a little bit easier to read, we introduced a 27th character, space. Okay, but the same concept. So we take this ciphertext, we decrypt with this key, this random sequence of letters, and we get this possible plaintext, Mr. Mustard with a candlestick in the hall. Then we keep trying. If we tried all possible keys, then another key, this random sequence of characters, we get Miss Scarlet with a knife in the library as a possible plaintext. It's the role of the attacker now to consider these plaintext values and say, which one was the original plaintext? Anyone know? What can you do? The only thing you can do is guess. In this case, if there are only 2 that made sense, then guessing gives you a 50% chance. But in practice, because there are so many keys, you'll get many, like in billions and billions of plaintext that make sense, and the chance of guessing when you choose from billions and billions is 1 divided by billions and billions, which is almost 0. So the attacker has no way to find the true plaintext, even if they do a brute force attack. And it's the only known cipher that has that characteristic, unconditional security. For this to work, let's say I had the original plaintext. It was Mr. Mustard with the candlestick in the hall. And I encrypted. I chose this key. To send my ciphertext to you so you can decrypt, I must somehow get the key to you. That's a challenge. Now consider if my plaintext was maybe 10 gigabytes. My key must be the exact same length, 10 gigabytes. So to get a 10 gigabyte message to you, first I must somehow get a 10 gigabyte key to you. And we must do that manually. Write it down on a piece of paper, encode it on a CD or multiple DVDs on a USB drive. That's very hard to distribute keys of such a size. So the problem with the one-time pad is if you want to encrypt large messages, you need a very large key. And distributing large keys is hard. Okay? That's the first problem. The other problem, the key must be random. It turns out creating random sequences, many long random sequences, is not easy, even for computers. So it's hard to generate many different random sequences such that we can have a key that is truly random. So the one-time pad is perfect in terms of security, but has 2 practical limitations. It's hard to create random keys, especially many different random keys, and it's hard to distribute random keys or long keys. Hence, it's not used much. It was said to be used by the Russians during the Cold War to send short messages to each other, because with short messages it's possible, because you only need a shorter key. But once you want to encrypt data, streams of data or large data files, it becomes impractical. So we've arrived at the perfect cipher, but because it's not practical, we need other ways to make ciphers secure. They may not be perfect, but they need to be both practical and secure enough. So later we'll talk about what do we mean by secure enough. All of these ciphers are what we call substitution ciphers. Replace one letter with another letter in the alphabet. Transposition is simply rearranging letters. A quick 1 or 2 examples. Rail fence transposition. Let's try it. We take the plain text and we write it across rows. So on the slide we had our plain text, and I'll write that plain text. The key is the depth. It'll make sense when we go through the example. We're going to write it across 3 rows. So 3 rows, row 1, 2, 3, Internet, Technologies and Applications. We'll get there. Technologies. Someone tell me when I make a mistake. And applications. Now all we do to encrypt or to obtain the ciphertext is read row by row. I'll write it in lowercase, it's easier. Read the first row. And then read the second row and then the third row. And I'm going to run out of space, but let's try it. A transposition cipher. So the key is the depth or the number of rows. If I had 4 rows or a key of 4, then I'd write INTE across those 4 rows and then come back to the first row. So we write our plain text in rows and then read row by row to obtain the ciphertext. That's it. It's a transposition cipher. It rearranges the letters. Each letter in the plain text exists in the ciphertext. We haven't substituted any. In the plain text, there is no letter Q. In the ciphertext, there's no letter Q. In the plain text, E occurs 4 times. In the ciphertext, it occurs 4 times. So we're just rearranging in this case. Again, very easy to break, given ciphertext. Basically, if you start to try different depths, then you can, again, look at possible or expected words and see if you try a depth of, if this is the ciphertext given to you, you'd maybe try a depth of 2 and write it using a depth of 2 and see if you can make words. If not, you'll soon discover you can't make words with a depth of 2. You try a depth of 3. If that doesn't work, 4 or 5 and so on. And it's not so hard to automate breaking such a cipher. But this is an example of a transposition cipher. Rows, columns, a different transposition, and it's slightly better. We have a key which indicates a number of columns. Plain text and key. So this one, the key was a depth of 3. In the next example, the key is, what is it, 3, 1, 5, 6, 2, 4. They're in fact the numbers 1 to 6 just mixed up. We'll see the significance. What we do is we write our plain text in columns. So we had security The number of columns is determined by the key. The key has numbers 1 to 6, so we'll write it in 6 columns. Security and cryptography. And we'll pad this out so that we have an equal number of entries in each row. Let's just add an X at the end, just to fill it out. So it's actually security and cryptography X. We need to have the same, or each row filled out. To get the ciphertext, we read the columns, but according to the ordering. So we'll read the columns like STRR, but we don't read this column first. We read the column which is number 1, EYYA. So the ciphertext, and I'll write it below, EYYA, this column, then RDOY, the key tells us which column to read. Then STRR, ICGX, X, that is, CAPP, and UNTH. There's our ciphertext. Just a different transposition cipher. Write our plaintext in across a set of columns, and then to get the ciphertext, read the columns as indicated by the key. The key must be, if we want 6 columns, 1 to 6 rearranged. If we can have a different length key, it can be 7, 5, 3. That's up to whoever chooses the key. Again, the plain text letters appear in the ciphertext. Frequency analysis, we haven't changed the frequency of letters. If there were 12% of E's in the plain text, there are 12% of E's in the ciphertext. So that doesn't help. The transposition doesn't change the frequency statistics. But it turns out applying transpositions combined with substitutions can be used to build very secure ciphers. And we'll see that in the next lecture. We'll return and see that 2 concepts. One is that this one's easy to break. It's not so hard to break if you have just the ciphertext. But if you apply that same encryption again on EYYRDOY, that is, write that in a sequence of columns and rearrange, then it will be harder to break. Multiple operations, multiple applications of the same simple cipher makes a cipher secure. And combinations of transpositions and substitutions can make a cipher secure. So we'll get to that next lecture. So make sure you can do the 7 classical ciphers that we've gone through today and last week. We'll continue next lecture.